Hey, recording's rolling. It's Tuesday, February 3rd. So I'm gonna do something a little bit off the beaten path today. Right. So the content we cover today probably won't strictly show up in AP questions, but I do want you guys to know about the same way. Plus, you get a really cool lab. You guys get to get your hands on some tuning forks and some pipes. Here, I'll show you guys in a few minutes. Well, I'll leave it with this. I want you guys to know a little bit about Doppler effects, look at that, some demos related to that. I'll show you guys how to do this speed talent. Guys, let's go here. Guys, by the time you walk out of class today, you will have calculated the speed of sound based on measurements. You guys be looking for quiz coming Monday on simple harmonic. It's just going to be a simple harmonic motion question. So if I think you can show up on the AP exam, then those are the kind of questions that will show up on Monday on that quiz. All right. And guys, what are we doing tomorrow? Debrief AP classroom. A bunch of guys have already turned this in, so awesome if you have. All right, let's flip over to Paul Hewitt. I think it's a good way to kickstart this right here.
You're like a bird, you're looking right down in the water. There's a bug sitting there. And this is a lake that's perfectly smooth. But now what the bug starts to do is the bug starts to jiggle up and down. And when that bug jiggles up and down, that bug is a vibration, yeah? And that's vibrating on a nice surface, yeah? We're going to make what? Begin with a W. All right. We're going to make waves, gang. We're going to make waves, okay? And the waves kind of look like this. Where I draw the line, that represents like the crest of a wave, like it might sort of be like this. Can I see what I'm saying? Okay, so this represents the crest of the waves. And the waves go out in all directions. And the fact that they're circles is kind of evidence that they go out in all directions at the same speed. Isn't that true? Like if it went faster over here, then the wave would sort of be like that, yeah? Okay, so the circles are evidence of the same speed, okay? Now, what would be the frequency of the waves compared to the frequency of the vibrating bug? In other words, if you put your hand here, blip, 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 the waves would hit your hand, yeah? Certain frequency. How would that blip, blip, blip compared to the whoop, whoop, whoop of the bug? Same. Isn't that right? The frequency of a wave is the same as the frequency of the vibrating source. Makes sense, doesn't it? Let's suppose now that the bug swims in this direction. What the bug is going to do is the bug is going to swim in the direction of the waves that it's producing, and it continues to vibrate a little bit, yeah? Wouldn't the wave pattern look something like this? Can kind of be seeing that? In fact, what direction would the bugs be swimming, gang? I mean, you can tell it's going that way, right? Well, the bug might be at rest and the water's going this way. I mean, motion is relative anyway, yeah? Okay, now if I put my hand over here, would I get a higher speed wave, a lower speed wave, or the same speed wave? Check your neighbor. And make sure you're listening to the question that's being asked.
The question being asked, something about the speed of the wave, right? Here, give you guys a hint. Guys, look at those, the crest of those waves right there. Are those still circles? Yeah, right. Right, which is maybe evidence that once the bug has released that energy into the water and propagating, it's just going at that point, right? It doesn't really care about the motion of the bug anymore. Right? So what do you guys think about the speed of the wave? What happens to the speed of the wave?
How many people say, hey, the speed of the wave is going to be the same? Yeah, that's right. The speed of the wave doesn't change. What does change, gang? How frequently that wave encounters you is different, yeah? So I can get a different frequency. When I put my hand here, higher frequency or lower? Can you see it? Over here. Bloop, bloop, bloop. That change in frequency due to motion of the source or the receiver is what we call the, named after a person. Okay, good. It is called it's a Doppler effect. That's right. The Doppler effect is the change of frequency when something moves toward you, away from you, that sort of thing. The change of frequency due to motion.
All right, and the equation goes with this. Right, so really, we're focusing on frequencies, right? Maybe this car has a horn going like beep beep, and if you're inside the car, you hear beep beep. Right? It doesn't matter how fast the car's moving because you're moving along with the car and pocket it around the car. Okay? But what about this observer here? Now the car's driving towards him. Okay? I mean, here's maybe what it sounds like. Beep 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 beep. You guys hear that pitch shift? Right? And here's a good equation. Okay. You guys see some plus minuses? right? The plus or minus, well, we're talking about velocities, right? Is the car headed towards the person or away from the person, right? After it passed the person, right? We got speed of sound, right? There's velocity source and velocity of the observer, huh? Right? Hey, I bet this guy could also be running back and forth too if he wanted to be, and maybe that could change the observed frequency compared to the source frequency. Beep 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 beep, something like that. Right here, let's just do a little equation here. So the observed frequency is equal to the source frequency, right? Multiplied by, okay, you get this big ratio, right? So speed of sound, plus or minus velocity of the observer, divided by speed of sound, plus or minus velocity of the source, maybe the car in this case. Okay. Now, I'll throw some numbers to you guys. Okay, suppose the frequency of the car horn was about 300 hertz. 300 hertz. Whatever sound that could. Hey, that could be a musical note. I connect to this one later. Okay. Now, I'll give you guys a nice ballpark speed of sound. Okay. Oftentimes it's rounded to about 340 thereabouts meters per second. You know, plus or minus. It depends on the temperature and the pressure, and this is kind of particular to maybe like approximately room temperature at sea level. Okay, so this shows up two places. Okay. Now, guys, let's say that if this guy is stationary, he's just standing there. What would velocity observer be? Yeah, 0. So we'll put 0 meters per second for a velocity observer. Okay. Let's say the car is traveling towards this guy at, right, so I'll say car travels toward the observer. Okay. And let's throw a number at it. How about 5 meters per second? Okay. Yeah. Now to finish this calculation, you guys got to figure out, is this going to be a plus or a minus right here? He's traveling toward it. Okay. Now I like to work this out logically. Guys, if the car's traveling towards the guy, does this guy towards this observer? Okay. Does the observer perceive a higher or lower pitch than usual? Yeah, it'd be a higher pitch. Right. So this frequency, the numerical value has to be what? Larger or smaller than 300 hertz? Has to be bigger than 300 hertz. Yeah, maybe it's like 310 or 320 or something. Okay, so we're going to find out. Okay. That's being more than 300. But how do you get more than 300? Well, if everyone was just sitting at rest, speed of sound over speed of sound would simplify to 1. So you would perceive the same frequency. But we want to make this value larger than the original 300. So do you get that by adding or subtracting on the bottom? Subtracting. Yeah, you have to subtract down here. Okay, you guys see the logic behind that? There's other ways you can navigate and reason that there have to be minds there, but that's why I like to do it myself. So let's throw this all in the calculator. Make sure you can correctly group parentheses and the whole thing. So 300 times, we got 340 divided by, and then definitely put some parentheses right here. 340 minus 25. I'm looking at the observed frequency being 323.8 hertz. Yeah. So higher frequency. All right. So you guys good with Doppler? Okay. All right. Now, is it possible that this car could be traveling faster than the very waves it's just sending out? Like the speed of sound is what I said 340 about meters per second. But if you put rocket boosters on this car, could anything travel faster than 340 meters per second? Yeah. I mean, what if you have like a rocket or something? Okay. You guys ever heard Mach something? Mach 2, Mach 3? Okay. What do you think is meant by Mach 3? 3 times the speed of sound. Right. And now here's a bunch of individual waves going out. Right? But now this plane in this case is traveling faster than the very sound it's sending out. Right? What shape does this? Think in 3 dimensions. What shape is this right here? A cone. Right? If you were an observer, suppose you're standing on the ground right where my pin is, right here. Right? The plane is already past you, above in the sky. Right? You see it past you. Has this guy heard the plane yet? No, because none of the sound has reached him yet. Right? And when it does, he hears a what? Sonic boom. Yeah, sonic boom. Hey, here, see, get some. You're gonna see some cone clouds here, right with the yeah. You guys saw it cone right there. Saw it cone. Ah, so it's kind of a flat tone. Maybe it's just a little faster than speed of sound. Right, there you go. All right. Let's do Rubens too. All right. So now you guys know, guys, sound is sound a pressure wave. So if he throws a, now he's gonna throw a very neutral sound over just a sine curve. Right. Get rid of all the timbre.
Let's start with a 449 hertz frequency.
Ooh, okay. Now at this point right here, do you think this would be a higher or low pressure point, pushing down the flames? High pressure. Ah, what about right here, vacuuming up the flames? Probably low pressure, right? You guys can see how you can pick out the wavelength, right? If you do the speed of sound, maybe that could correspond to that frequency that he named. Right? What if he changes the pitch? You guys see the pitch going up and see the wavelength getting shorter? Ooh, that's kind of cool. All right. All right. So. I forgot to show you guys one more thing on Doppler. Let me go back to Doppler real fast. Okay. So this was here, guys. This was Doppler effect for sound. This type of equation pairs with it, right? And I don't. Objects can't travel faster than the speed of sound. That's probably what it says. This type of action. Okay. Now, here's a corner of physics we haven't quite gotten to for this class. Guys, can anything travel faster than the speed of light? No. No. Right. So it's physics of relativity. When you speed up and you start to approach the speed of light, you get these weird time dilations and things. So you can always speed up, but you can never reach the speed of light. That's a weird thing. Right? If you look in the sky and you see distant galaxies that are either redshifted or blue shifted, it tells you something about the relative motion of the galaxies, and you can calculate how fast. Well, usually it's expansion, universal expansion. The vast majority of galaxies relative to us are, what do you think, red or blue shifted? Red shifted. Yeah, Edwin Hubble figured this out about 100 years ago. Oh, hey, that's evidence for universal expansion. And you can back calculate how long ago was everything one place one time. It's about 14 billion years. Yeah. Right, so back to sound. Right. Now here's two categories of waves. Sound is properly which one of these again? What sound? Is sound a pressure wave, like longitudinal wave? Yeah. All right, let's see, like high pressure, low pressure. These could be like individual air molecules. Okay. It's really hard to draw this properly because you got to sit here and do like dot densities and all kind of thing. Okay. So oftentimes, people just whip off a transverse wave because it's so much easier to draw, and that's supposed to represent this. All right, so you can see something like that. Actually, you will today. Okay, you guys see this wave going on right here on your paper? That's really a representation of what's supposed to be a longitudinal. You guys get that right? There's a mouse on. All right. So kind of same thing with these waves here. All right. Yeah, let's do a couple more quality units. Switch over.
Oh yeah.
It's literally.
Let me get these things so they're a little bit different in frequency. And strike them both at the same time. Can you hear the throbbing? That is a result of interference, and the phenomenon is called beats. All right.
Beats.
Hi gang, sound time. If this room were filled with ping pong balls and I had a big paddle and I shook it back and forth, I'd send vibrations through those ping pong balls. Same type thing happens when I strike this tuning fork. This vibrates back and forth and hits the air, and the air vibrations, that's what you pick up as sound. Here I have a fork of frequency, same. Watch, listen at me. Strike this one vibrates. Or, as long as the frequencies are matched, I can get the vibrations to cascade back. It's called resonance. Huh? What happens if this fork has a different frequency? Let's try now. Yuck, nothing. I have to have this frequency the same as this to pick up the vibrations from here. That's what happens with a radio set. Your radio signals are coming in and you change the frequency of your radio set so that it matches the incoming frequency. You got it. Physics. Yay.
Physics, yay. All right, here's getting now closer to lab. All right, so there are these boxes of tuning forks back here. Boxes of tuning forks. All right, got a whole set here. All right. Now, I was trying to figure out what tuning this is. I don't think these are either Pythagorean or equal temperament, which is the two systems I got here. Here's Pythagorean ratios. Here's equal temperament. I think I showed you guys the other day. These are fairly similar, but they're off a little bit from each other. Okay? I think these are called scientifically tuned. I don't know the whole story behind it. Okay? And for this particular lab, it's kind of hard to get the bigger ones to work with us just because of the length of the pipe on it. So here, I'm going to pick this one. Now this one's labeled G. And it says 384 hertz. But again, I think that's particular to whatever tuning system that they have going on here. All right, so pull that out. Okay? And what I'll do is I can strike this. Okay? No, don't strike it too hard. Don't warp it. All right, you guys can hear that tone? All right, so that's 384 hertz. Now, if I hold this over a PVC pipe over water, which I got back here. Right? So I got these beakers of water. Right? I got these PVC pipes right here. PVC pipe. Now I'm going to strike this tuning fork over this pipe. Okay. Then I can raise and lower the pipe in the water. Now the water is going to effectively close one end of the pipe, isn't it? Right. And at some point it's going to resonate, and I want you guys to hear it. It'll be like, it'll resonate. Okay. And when it does, what kind of pressure do you think is right above the water line? A high or a low pressure? High pressure. What do you think is right at about the mouth of the pipe? Maybe a low? Right. I don't know if this will show up on video, but I think you guys can hear this here. Here. Right there. You guys hear it resonate? Hear it resonate? Okay. What I can do is I can take either a ruler or a meter stick, and I can measure from the water line up to the top of the pipe. Right, and I can grab this distance right here. Is that? Okay. Now, I'm just gonna make some. Suppose that was like 10 centimeters. I'm just making some. I don't know if it was. Right. If that was 10 centimeters for Solon tuning fork, approximately where should you be hunting around for the second place that'll resonate?
20?
Not 20. 30. Guys, does this look like 3 times this? Great. And it might not be exactly 3 times, but it might be fairly close. Okay, so show you guys what's going on here. Right, so here's the same setup. Right, same setup. Right, so here, if you just follow these boxes in order, then it'll lead down to ultimately your goal is to quantify, to calculate what is the speed of sound in meters per second. Right? Actually, I told you guys earlier today it should be roughly 340 meters per second, so somewhere there. So first box, pull the number straight off the tuning fork. Like this one says 384 hertz. So I'd write 384 hertz. Right, you guys get that? Okay. L1, which is labeled right here, that's the first distance that resonates. Suppose this comes out to like 10 centimeters. Guys, how many meters would that be? 0.10. Right, 0.10. Right. And then I'd be hunting around approximately the 0.30 meter area. Right. It might not be exactly, it might be close to a little bit. Right. And some of these pipes are, well, the pipes might be too short, so you might have to stack a couple of pipes. Right. Can you guys stack a couple of pipes right on top of each other? I don't have a second one in front of me, but you need that. Right. Now, when you get these two lengths, next box right here, this fourth box, says to take the difference. Guys, if you do this big L2 minus this little L1, okay, do you guys see this as, guys, how many wavelengths, here, let's start with short one. How many wavelengths total do you see right here? 1/4. If that's 1/4, what is this right here? How many wavelengths? 3/4, right? It doesn't quite complete one wavelength. Right? So then if you subtract the two right here, guys, what's 3/4 of something minus 1/4 of something? 1/2. Right? So should this value right here represent half of the wavelength? Half wavelength? Right? And then next box says go ahead and double that. Oh, well, if the difference represented half wavelength and you turn around and double that, this distance right here represents what? One wavelength. Okay. And finally, to bring this all together, last box right here. Okay. Speed is wavelength and frequency. Okay, so the last box we've just found at this point is effectively the wavelength. Okay. The frequency is the number straight off the tuning fork in hertz. As if you multiply those two together, that gives you the speed of what again? Speed of sound. Okay. The speed of sound should be the same for all the tuning forks. Should be the same for my voice right now going into your ears. Yeah. Speed of sound is whatever it is in this room. Whatever. Yeah. Corresponds to whatever temperature pressure. Okay. All right. Any questions? All right. So you guys got the rest of the class to do this lab and turn it into the gray tray.